Hello, this is Prabhu Shah. I'll be presenting a talk on my paper titled Voting-Based Opinion Maximization. This work was done while I was a PhD student at NTU in Singapore. Let's begin with a discussion on the well-known influence maximization problem. Here, we have a social network where initially, apart from some seed users, all other users are inactive about a particular campaign, as shown in the figure on the left. The black color denotes the status of being active. Eventually, as the information propagates in the social network, the other users may get influenced by the seeds to become active, as shown in the figure on the right. Given this, the goal is to find seeds which maximize the expected number of influenced users eventually. However, this setting suffers from some drawbacks. For instance, a user can be either active or inactive, and nowhere in between. Second, a user can only switch from the inactive state to the active state and not the other way around. These issues can be resolved by a voting-based opinion maximization problem, where each user has real-valued opinions about a particular campaign. The seeds have the maximum possible opinion value. Eventually, as the opinion diffuses in the network, each user updates his or her opinions according to those of his or her neighbors. Note that here a user's opinion can decrease with time, as has happened to the lower node in the middle. Given this, the goal is to find the seeds which maximize a given voting-based score over the user opinions. Let's now formalize our problem. We adopt the well-known Friedkin-Johnson opinion diffusion model, where for any candidate CQ, each user U has an opinion BQUT at time t, which is at least 0, and a stubbornness. And between every pair of users, there's an influence weight. These weights are such that for every node, the incoming edge weights add up to 1. Given this, the opinion of user V about candidate CQ at time t plus 1 is given by this recurrence relation. This can be interpreted as the user V adopting his or her own initial opinion with probability equal to the stubbornness, and otherwise adopting the weighted average of the incoming neighbor's opinions in the previous time step. As an example, consider the social network in the figure on the left, with initial opinions, stubbornness, and influence weights, as shown in the tables in the top row. Using them, we can compute the opinions of all users at time 1, as shown in the table in the bottom. We particularly illustrate the computation of the opinion of user 3 about C1 at time 1, according to the equation in the previous slide. Using that, the opinion turns out to be 0.6. We now discuss voting-based scores, which can be computed by aggregating all users' opinions for a candidate at time t. Now, this aggregation can be done in various ways. For instance, the cumulative score simply sums all the opinions, and the plurality score denotes the number of users which prefer that candidate to the others, and the Copeland score is the number of other candidates whom this particular candidate defeats one-on-one. Some properties of our scores. It turns out that all three of our scores are non-negative and non-decreasing. We prove that the cumulative score is submodular while the others are not. Now state our problem. Let's consider a target candidate CQ for whom we are looking for seeds. And for the seed users, the setting is that we set the initial opinion BQU 0 and the stubbornness DQU to 1. With this setting, we aim to find at most case seeds which maximize a given voting-based score for the target at a given time t. This problem has applications in scenarios where there is a voting for all users, and the winner among multiple candidates is chosen as the winner. For instance, a parliament vote, a plebiscite, or even a referendum. We have proved that this problem is NP-hard for most of our scores. How do we solve this problem? We use the standard greedy algorithm, which iteratively adds seeds till the size reaches k, and each iteration it chooses the node with the maximum marginal gain in score as a seed. Since our cumulative score is submodular, this algorithm turns out to have a 1 minus 1 over e approximation guarantee for that score. And for the other scores, we can also provide guarantees using sandwich approximation, which we'll talk about later. Now, the previous problem involved maximizing the score, but that does not guarantee that the target will win against the others. So to ensure that, we solve a new problem, which is to find the minimum seed set size K star such that the target wins. So how do we solve this problem? Well, recall that all our scores are non-decreasing and the minimum value K star can only be between 0 and n. So we use a binary search on the possible values with the initial minimum as 0 and the maximum as n. For the value midway between the two bounds, we apply algorithm 1. If the candidate wins for that value, then we set the maximum value to be equal to the current value and repeat the process. If the target loses, then we set the minimum value to be equal to the current value and repeat. Now here for the current value, the target wins. And now the bounds have converged. So the current value is returned as the value of K star. We now discuss the sandwich approximation technique, which provides approximation guarantees for non-submodular functions also, as we said earlier. Suppose our score f is non-submodular and it is sandwiched between an upper bound ub and a lower bound lb for all possible values. And suppose we can provide an eta and tau approximate solution to the two bounds. Now, is it possible to use this information to provide an approximation guarantee for f? The answer is yes. We simply compute any feasible solution for f and return the following solution. The challenge here is to design suitable bound functions so that the first two steps, which is computing the eta and tau approximations, can be run. For our scores, we choose non-negative, non-decreasing, and submodular bound functions that both eta and tau are 1 minus 1 over e. The bounds are as shown here. Note that the computation of the lower bound for the Copeland score is an open question for future work. Now, it turns out that computing the exact marginal gain in the score for every iteration of the greedy algorithm is expensive. So we resort to approximating the opinion of each user U at time t, and hence the score using reverse random walks. Let's illustrate that with a small example. Consider the same social network as before, and say we want to approximate the opinion of user 3. Starting from 3, with probability equal to its stubbornness, the walk terminates there itself, and otherwise, according to the influence probabilities, it transitions to one of its incoming neighbors, say 1, and the process is repeated. This continues for t rounds, and eventually the estimated opinion of the user at time t is simply the initial opinion of the end node of the walk. Using this, we design our random walk-based method, where for all users in the network, we generate some random walks. And after that, we run the same greedy algorithm. In that, we truncate all the walks at the chosen seed node according to the estimated marginal gain. Now, the number of walks per node, lambda v, is specific for each score, as we show. Let's now analyze our method. The time complexity for the other scores is the same as that of the cumulative score, plus the time needed to compute the opinions of the other non-target candidates. And as far as the accuracy is concerned, we do get accurate estimates with probability at least rho if lambda v satisfies the following conditions for each score, as stated here. Coming to our sketch-based method, it is a further optimization to the random walk-based method, in that instead of starting from all nodes in the network, we only sample walks starting from theta randomly chosen nodes, where theta is less than n. And the remaining algorithm remains exactly the same, which is we truncate all walks at the chosen seed node in each iteration. Even here, the values of theta and lambda v are specific for each score. The time complexity for the sketch-based method is similar to those for the random walk-based method, except that it takes into account the fact that we only sample from random walks from theta randomly chosen nodes. As far as the minimum value of theta is concerned, the details can be found in the paper. In particular, we point out the one for the cumulative score, which is that if theta satisfies at least this value, then our algorithm with a high probability has a 1 minus 1 over e minus epsilon approximation guarantee. We run experiments on real-world data sets to illustrate the efficiency and effectiveness of our methods. In particular, we compare three proposed methods, which are the greedy algorithm based on direct computation of opinions, the one based on random walks, and the one based on sketches, with these existing works as shown here. Let's now analyze the efficiency and effectiveness of our methods. We evaluate the effectiveness based on the corresponding scores, cumulative, plurality, and couplet. Note that our three methods, DM, RW, and RS, outperform all the baselines for all the scores in terms of effectiveness. And as far as the efficiency is concerned, the running time of RS, which is the one based on sketches, is much lower than those of the other two. And all our three proposed methods run within a reasonable time. Hence, we recommend our sketch-based method as our ultimately proposed method. We also run experiments to find the number of Cs needed to win. Notice that we cannot compute the exact opinions, so we resort to approximate methods, DM, RW, and RS. And also notice that as the method becomes more approximate, the minimum number returned increases. This is understandable because for a more approximate method, the estimate of the score is less accurate, which means the minimum number required to win can only increase. To summarize, we investigate the problem of maximizing a voting-based score at a given time horizon where real-valued user opinions diffuse according to some specified model. For non-submodular scores, we propose the greedy algorithm coupled with sandwich approximation to provide approximation guarantees. We further optimize using random walk and sketch-based methods. And the sketching-based method is the ultimately proposed one, since it is reasonably accurate compared to the others and much faster than the others. In the future, it would be interesting to consider more opinion diffusion models and voting-based scores. Thank you.